SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the third lecture. Okay, so in the last class we learned about traction vector, and today we are going to learn about another new concept, that is of the stress tensor. So, let me begin with the last result that we had. So, we found out the formula for traction on an arbitrary plane with normal n, and we said that this is equal to the following quantity. So, basically this formula tells us that if we know traction on any three planes at a point T1, T2, T3, then we can find out traction on any arbitrary plane at the same point, which is Tn in this case. All right. What we should note here is that while deriving this, the body force term and acceleration terms dropped out. So, this formula is going to hold even if the body force is present or the body is accelerating. So, let me just write it down, that this formula holds even if body force is present or the body is accelerating. Let me draw this picture again. So, we have an arbitrary body and we want to know traction at a point, and suppose the plane here, that is the plane with normal n, and you see, to find out traction on this plane we used traction on three planes T1, T2, T3, but see physically this Tn, the traction on this plane with normal n, has to be the same irrespective of what three planes were used to find out the traction. So, what I mean to say is that, like in this formula that you see here, we have tractions on T1, T2, T3 which are E1, E2, E3 planes. So, if you choose any other set of planes, the final result would be the same. So, that comes from physics, that Tn, which is equal to Ti n dot Ei, this will be same as some Ti hat and n dot Ei hat. Okay. So, in the first case, the planes used here are E1, E2, E3, whereas in the second case the planes used are E1 hat, E2 hat and E3 hat. See why they are same, because it has to be same from physics, it is the same plane n. So, whatever three planes you use to get this Tn, it has to be the same. Okay, so let me write this down also. the above formula for T n is independent of what three planes were used. Okay. So, that is just a recap of what we have done till now, and as I told you, we now want to discuss about a new concept, that is a stress tensor. Okay. So, let me try to write down this formula only, but in a slightly different way. See, what we have here is T n equals I equal to 1 to 3 T I n dot E I. Now, n dot E I is same as E I dot n. So, I am going to write this as I equal to 1 to 3 T I E I dot n. Okay. No problem here, because the dot product is commutative, you can change the order. And then you see, let me try to write down in the column form. So, T I is a vector, so it becomes a column. So, that is T I, and in 3 dimensional space it is a 3 cross 1, it has 3 components, 3 cross 1, and then we have dot product of E I and n, and to dot product you can recall from the first lecture, I have to take the transpose of the first vector and then multiply with the second vector. Okay. So, let us take the transpose of E I, so it becomes a row. So, this is basically E I transpose, and then multiply this with n, the column n, all right. So, this is n. So, we have to first do the dot product. So, the E I transpose into n has to be done first. So, basically these two are same. Okay. So, you see on the extreme right side we have 3 cross 1 T I, then 1 cross 3 E I transpose and 3 cross 1 n vector, and you can see within the bracket this 1 cross 3 and 3 cross 1, when you multiply it gives you 1 cross 1 a scalar quantity, the normal dot products, right. Dot product gives you a scalar quantity. Now, you also know that matrix multiplication is associative. So, you could also write this as so this is T I and then E I transpose. So, we first work out the product of these two and then multiply with n. Okay. So, this is a different viewpoint. So, what happens now when you multiply the first two together? So, the first one is 3 cross 1 and this is 1 cross 3. You can recall from the first lecture that this is actually the tensor product of two vectors, because this is giving me finally a matrix. This is finally a 3 cross 3 matrix. So, dot product of two vectors gives me a scalar, whereas tensor product of two vectors gives me a matrix. So, this is actually a tensor product. Right. So, I go back to the vector notation, and I could write this now as summation over I equal to 1 to 3 T I tensor product E I multiplied by n. See, very simple. So, I started with, you see what we had earlier, T I n dot E I. I started from here and I got the final result also. So, these are two different viewpoints, but the nice thing about the final result here is that the orientation n has been separated. See, you have T I tensor product E I, which is together, and then you multiply with n, right. So, the orientation n has been taken out, and it is this thing inside the bracket which we will call a stress tensor. Okay. So, this is a stress tensor. And we are going to denote it with sigma and with a 2 tildes below. It is a second order tensor. So, with a 2 tildes. Okay. So, finally, we have a very simple formula now, that T n is nothing but sigma times n, and you remember that T n, which actually depends on what point in the body we are looking at and on what plane at that point. So, it depends on both x and n. So, on the right hand side, the sigma only depends on x, and the n dependence is now explicitly out, you see, sigma times n. So, it is proportional to the normal vector n. Through this formula, we have actually found out the expression for the stress tensor sigma, which is, as we wrote down above also, summation over I equal to 1 to 3 T I tensor product E I. So, basically, to obtain stress tensor, choose three independent planes at a point, find the tractions on those planes, do their tensor product and sum. Very simple. And as I told you, these three planes, if you choose another set of three planes, the summation has to be the same. So, the stress tensor is independent of what three planes you choose. Okay. So, I am also going to write it here again. Stress tensor is independent of what three planes we choose. All right. Okay, so that was the tensor but we would like to know how does that tensor look like, how does that matrix look like. Just like for vectors, let us say we have a vector v like this in the space, and if we choose a coordinate system E1, E2, E3 such that it is aligned along E1. So, suppose I choose this coordinate system E1, E2, E3. So, the vector v is aligned along E1. So, if you want to represent this vector in this coordinate system, in E1, E2, E3 coordinate system, then we get a column v, and then this column for E1, E2, E3 coordinate system, that is simply going to be v 0 0, because the vector is now aligned along E1. So, it only has E1 component, whereas if you choose another coordinate system, okay. So, this is E1 hat, E2 hat and E3 hat, which is same as E3, all right. So, in this new coordinate system, the representation of the vector v will be different. So, I will say the same vector v, when you try to express in the E1 hat, E2 hat, E3 hat coordinate system, then it is going to be different now. So, it is v by root 2, v by root 2 and 0. So, it has got both first two components are non-zero. That is because we are now choosing a different coordinate system to represent the vector, but you see the vector is the same. For both the cases we have the same vector v, the vector has not changed. Okay. So, that was with the vector. Similarly, we have now tensor, stress tensor, it is a second order stress tensor. So, how to represent the stress tensor in a coordinate system, that is the question now. So, we have the sigma, which is equal to summation over T I tensor product E I. Let us try to represent this in E1, E2, E3 coordinate system. Now, as you know that the stress tensor is a second order tensor. So, its representation is going to be a matrix. For vectors it is a column, but for tensors, second order tensors, it is a matrix. Okay. So, sigma its representation. So, we will use big brackets to denote that we are going to write down the representation of the tensor, and here in the subscript we say which coordinate system. So, it is E1, E2, E3. So, that is equal to summation I equal to 1 to 3 T I. So, let us represent T I in E1, E2, E3 coordinate system. So, this is going to be some vector T I and tensor product E I, and you know that if it is tensor product, that means I have to do the transpose of the second vector. So, this is basically E I transpose. Okay. Now, let us write down the 3 terms in this sum separately. So, this is T 1 into E 1 transpose. Now, how will E 1 look like in the E 1, E 2, E 3 coordinate system? It is going to look like 1 0 0. If you use some other coordinate system to represent E 1, then it will look something else. Okay. Then we have the next one, T 2 into E 2 transpose. So, E 2 transpose is now 0 1 0, right, and then the last one T 3 into E 3 transpose, which is 0 0 1. Now, you see each of the 3 terms here is going to give me matrix, and you have to sum those 3 matrices to get your stress matrix. What will the first term give me? What matrix is the first term going to give me? So, from the first term T 1. So, of course, it is T 1 is 3 cross 1 multiplied by 1 cross 3. So, we get 3 cross 3 matrix, that is trivial. But when you work out the matrix multiplication, you see that only first column arises from here, the next 2 columns are actually 0. If you write down this T 1 as T 1 1, then T 1 2, and finally T 1 3, the 3 components. Okay. So, first column multiplied with 1 0 0, when you work this out, you simply get T 1 1 1 2 and T 1 3 in the first column of the matrix. The other 2 columns will be 0. You can check this, just work out the vector times row, and this is what you get. Okay. Likewise, when you work out the second term, you get 0 0 0 and T 2 1, T 2 2 and T 2 3. Also remember that when I write here the representation of the traction, the components are simply scalar. So, actually I should get rid of the tilde from below. So, I have to remove the tilde because they are scalars. Likewise, from everywhere else the components are scalar. So, the tildes have to be removed. So, let me complete this matrix. So, this is 0 0 0, and you can now guess what is the third matrix going to be. So, when you add the 3 matrices, the final stress matrix sigma. So, the representation of the tensor with the big bracket. So, the final stress matrix is going to look like T 1 1, T 1 2, T 1 3, T 2 1, T 2 2, T 2 3, then T 3 1, T 3 2 and T 3 3. So, that is the representation of the stress matrix. If you want to write down the stress matrix in E1, E2, E3 coordinate system, then the first column has to be the representation of traction on plane whose normal is first coordinate axis, which is E1 in this case. Right. Similarly, this is for the second coordinate axis, and this is third coordinate axis. Now, this thing that you see here, many places you will see they will write it as what is T11, T11. So, that is traction T1, which is the traction on E1 plane, and you dot with E1 to get the component along E1. So, likewise for T I j, traction on ith plane and you find its component along E j. So, that is T I and dotted with E j. Okay. So, here we got a different notation that is usually used in the book. So, T11 is denoted by sigma 1 1, T22 is denoted by sigma 2 2, T33 is denoted by sigma 3 3. Okay. How about T21, the traction on second plane and its component along E1 direction. So, T21 that is denoted by tau. So, off diagonal components are denoted by tau and the diagonal components are denoted by sigma. I will tell you also why we use different symbols. So, this is tau 1 2. So, this becomes tau 1 3, tau 2 3, tau 3 2, tau 3 1, this is tau 2 1. All right. Now, if you see carefully, then tau I j, what do I and j mean? So, j, the second index, denotes the plane normal. So, this is to denote the plane normal. Whereas, the first index is used to denote the direction or the component of traction. Direction of component. So, traction on j plane and its component along ith direction. Okay. I could write here traction on j plane and take its component along ith direction. So, that is tau I j. Okay. Sigma 1 sigma 2 sigma 3 are trivial. So, sigma 1 means traction on one plane and its component along the one direction itself. All right. There is also a very nice picture denoting those components. So, in books you will find they say representation of stress tensor in Cartesian coordinate system. So, Cartesian coordinate system means our axes are E1, E2, E3, perpendicular axis E1, E2, E3. Okay. So, at a given point, so we have this body and I want to know the stress tensor at a given point. So, that is the point x. So, at that point how does the stress matrix look like, and I want to represent it in Cartesian coordinate system, that is in the E1, E2, E3 coordinate system. So, our planes are E1 plane, E2 plane and E3 planes, right. So, we think of a cuboid around the point x. So, draw a cuboid around the point x. So, it has 6 faces, one along E1, then along E2, then along E3, then along minus E1, minus E2 and minus E3. Okay, and the center is the point x. So, that is the point x where I want to get the stress. So, this cuboid has to be infinitesimal, so that the planes are very close to the point x. Okay. Let me zoom this cuboid. So, I make a very bigger cuboid, all right. So, it has those 6 faces along E1, E2 and E3. So, here is the coordinate system E1, E2 and E3. So, on E1 plane you see this is the E1 plane, that is the E1 plane. The traction that acts on E1 plane is T1, right. So, we have T1 here, and it has 3 components, the component along E1, the component along E2 and the component along E3. The component along E1, so that is going to be denoted by sigma 1 1, right. From our matrix we know it is sigma 1 1. The component along second direction along E2, that is tau 2 1, is not it, from our matrix you can see, and the component along third direction, that is tau 3 1. Now, what can you say about the components here? Look from the picture, sigma 1 1 is normal to the plane, the component normal to the plane, whereas tau 2 1 and tau 3 1 are in the plane. So, we call sigma 1 1 the normal component of traction and tau 2 1 and tau 3 1 as the shear components of traction, because they are in the planes and they try to shear the body. Okay. So, think of two planes in the body which are very close to each other, and between those planes if we have the traction with the component along the plane, then that will try to shear the plane, displace the two planes along the direction of the plane itself, is not it? Whereas sigma 1 1 which is perpendicular to the two planes, if there is some sigma 1 1, so it will either try to push the two planes or pull the two planes, depending on whether it is positive or negative. If sigma 1 1 is positive, that means it is trying to pull the two planes apart, because it is tensile. Since traction there is positive, so on the top plane here, the bottom plane is going to apply traction such that it is pulling it towards itself, whereas for the bottom plane the top plane applies the traction so that it is pulling it towards itself. Okay. So, that is the pulling nature. So, that is the tensile nature. Okay. If sigma 1 1 is positive, that is the tensile nature of the interaction, and for tau 2 1 and tau 3 1 it is a shear. So, in the two direction, if there is some traction component in the two directions, so the shearing is going to happen along the second direction. If there is some component along the third direction, then the shearing is going to happen along the third direction. If you have the component in both the direction 2 1 and 3 1 both are there, then the shear will happen in some other resultant direction. Okay. So, we say sigma 1 1 is the normal component of traction. And positive means it is tensile and negative means it is compressive. So, positive means it is tensile and negative means it is compressive. So, tau 2 1 and tau 3 1, so these are the shear components of traction. Okay, and now you know what does shear mean. When two planes are sliding along the plane direction, that is shearing. So, whenever you have shear traction, the sliding can happen, right. All right. So, let me complete that diagram. So, we only drew the traction components on E1 plane. Let us do the same thing on E2 plane. Okay. So, on E2 plane, which is the top plane, we have sigma 2 2, the normal component, then we have tau 1 2, right. So, tau 1 2 has to be along the one direction. So, that is going to be like this, tau 1 2, and then we have tau 3 2. Tau 3 2. So, that completes the picture on E2 plane, and then we come to the E3 plane. On E3 plane, the three components are going to look as follows. So, we have one along the normal, which is the normal component. So, that is sigma 3 3, then along the one direction, that is tau 1 3. Remember that the first index is to denote the direction and the second index is to denote the plane normal. Okay. And then along the second direction, we have tau 2 3. Okay. What happens on the bottom plane? So, bottom plane is the one with normal along minus E2. So, what is t minus 2? So, t minus 2, and we have seen that t minus 2 is equal to minus of t 2. Right. And for t 2 we drew the three components, it is sigma 2 2, tau 1 2 and tau 3 2. So, on the negative 2 plane, the normal component has to point in the negative direction, negative 2 direction. Okay. So, it is going to be from here. So, that is sigma 2 2, but pointing in the negative direction, because you see t minus 2 is equal to minus of t 2. So, it is the same magnitude sigma 2 2, but pointing in the negative direction. Okay. And then we have tau 1 2, same magnitude, but pointing along negative 1 direction. So, that is tau 1 2. And for tau 3 2 again the same magnitude, but pointing along the negative 3 direction. All right. So, basically on negative planes we have the same values, but you have to change the direction. All right. So, you can now draw the picture for negative E1 plane and also the negative E3 plane, right. So, I am going to leave that for you guys. So, this completes this picture that we have here. Okay. Okay, what we should keep in mind is that although you see that the 6 planes that we have here are not all passing through the same point x. See on the left hand side the picture, we wanted to find out the stress matrix at the point x. So, the planes have to pass through the point x, right. If the planes are not passing through the point x, then we do not have the traction at that point. Now, to visualize that, we drew this cuboid such that the point x is at the center. That is just for visualization, but you should understand that these 6 faces are actually passing through the point x. So, the way to visualize that would be that you shrink this cuboid to the point x, so that all the 6 faces then start passing through the point x, and then you have these traction components on those faces, right, which you can relate with the stress matrix that you have here, right. Okay. So, I hope you got some idea of the stress matrix and stress tensor in this class. So, I think I am going to close here and let us meet in the next class again. Thank you.